evaluating limits analytically. All right, this is mostly where we're going to be spending our time this year is analytically. All right, yes, we talked about numerically and graphically already, but analytically is where it's going to be. Before we do anything on a limit, what should we always try to do first? Direct substitution. All right, and if it works, we all good. All right, so if it doesn't, if we get indeterminate form or a vertical asymptote, then we have to start doing other things. All right, but always we try to direct substitute. So if it's of a constant, limit is x approaches c of b. Well, if it's going to be a constant, it's going to be b all the time. If it's a variable, we substitute it in, so we get c. Again, if it's a variable raised to a power, who cares? So we just substitute it in. All right, so let's look at this first one. I have a limit as x approaches 2 of 3. Do I have anywhere to substitute 2 in? No, so what's my answer? 3. All right, it's going to be 3. It's that constant. All right. This next one, limit as x approaches negative 4 of x. Well, what do I try to do every time? Substitute in. So I end up with negative 4. This one, I have a limit as x approaches 2 of x squared. I try to substitute in, and even Josiah can get this. What's this one? 4. Look at that. All right. Pretty good? All right, we're moving. So again, all the things in mathematics will still hold true with limits. All right. So sometimes we break them apart. Scalar multiple, we bring that number out front. It's kind of like a coefficient. We can work with them individually on a sum and difference, work with them individually on a product, quotient, power, all that good stuff. So all the things that we've done in mathematics still hold true with limits. Here we go. The limit as x approaches 2 of 4x squared plus 3. Again, what do I try to do first? I direct substitute. Well, let's see if it works. I substitute in 2. So now I end up with 4 times 2 squared. 2 squared is 4. 4 times 4 is 16. 16 plus 3 is 19. I end up getting 19. If you had to show your work, that's fine. I'm cool with it. This next one, oh my gosh, I got a rational function. But again, what do I try to do first?
Substitute.
Direct substitute. Now, do we a lot of the time see a quadratic and want to factor?
Yeah.
Yes, and that's a good thing. Means you're on the right track. However, do we have to factor everything? No. We try to direct substitute first. So we substitute in 1. What do I get in my numerator?
4.
I get 4 up top. What do I get in my denominator? 2. Did it break? No, I didn't get 0 over 0 or a number over 0, so we good. So my direct substitution, I end up with my limit as 2. All right. Now we're going to take limits of composites. And again, a composite function is made up of 2 functions, basically. But on a composite, what do? We go from inside out. We go from inside out when we're evaluating a composite. So a lot of the times we need to take the inside of it and then work out. All right? So here we go. So if I have the first one, limit as x approaches 0 of tangent x. Again, what do I try to do first every time? I direct substitute. All right? And so if I direct substitute, I get tangent of 0. What is tangent of 0? 0. All right? So is it touching or is it just getting close? It's touching. All right, that's okay. All right, this next one I have a limit as x approaches pi of x cosine x. So what am I trying to direct substitute in here? Pi. Now, I'm going to write this one out. This is basically saying why are you getting a calculator out? We don't need a calculator. All right. So this is basically saying the limit as x approaches pi of x times the limit as x approaches pi of cosine x. All right. I'm going to write this one out. I'm going to kind of split it apart a little bit. So limit as x approaches pi of x is just what? Pi. That's just pi. And then if I substitute in pi for cosine, what's that? Cosine of pi is negative 1. So this is the same thing as saying pi times negative 1, which we know is negative pi. All right. I just wanted to split it up to show you that you can. All right, because sometimes you'll need to. This next one, I have a limit as x approaches 0 of sine squared x, or sine x quantity squared. All right. This is the same thing, and I'm gonna directly show it. This is the same thing as saying the limit as x approaches 0 of sine x squared. Okay, that's kind of how it's done here. So now if I do a limit as x approaches 0 of sine x, well, what is that? That's 0. That's 0. And so then I'd have 0 squared, and 0 squared is 0. All right, so that's really what happened there. All right, pretty good? All right, we're moving. All right, here we go. I need somebody to read this. This is a good nugget. Harsha's going to read for us.
Let C be a real number and let f of x equal g of x for all x does not equal c in an open interval containing c. If the limit of g of x as x approaches c exists, then the limit of f of x also exists, and as x approaches c, f of x equals limit of x approaches c of g of x.
All right, fantastic. So this is what happens here. I'm going to have this a couple times on your quiz on Friday. You get a simpler function. You get a simpler function all but at one point. Because at one point it's going to break. You're going to get a 0 over 0, right? And that makes a what? A whole. And remember, like when we factored things and we canceled things out, and we got a simpler function, that simpler function worked everywhere.
Yes.
Remember that? That's what we're going to be doing here. That's what that just says. Okay, so the limit you can actually do on the simpler function where you can't do on the other one. But it created that whole. All right, so let's look at this one. I have a limit as x approaches 1 of x cubed minus 1 over x minus 1. So what do we try to do first every time? We try to direct substitute. Well, what happened? I get 0 over 0. Crap. What just happened? I got a hole. Means we can't do it, right?
No.
We done? Just kidding. No, we got to keep going. All right. So what are we going to do? We're going to factor. We're going to factor. Now, this is a difference of cubes. All right. This is a difference of cubes. There will be another method that we'll learn at the end of the year. However, right now, we have to remember difference of cubes. So this is in the form of this a cubed minus b cubed thing. Remember? This is also on your summer coursework. So this is the same thing as saying a minus b times a squared plus ab plus b squared. All right? And then I'm going to go ahead and write the other one just in case. So if we have a cubed plus b cubed, that would end up being a plus b, and then a squared, and then we have minus ab plus b squared. All right? So that's what we're going to have to use at the beginning of the year. Okay? At the end of the year, we will have another tool in our toolbox named after a French dude. But anyway, right now, that's our tool. Okay? We're going to factor it. So what does x cubed minus 1 factor to? We're going to use this. X minus 1, and then x squared plus x plus 1. And then it's over x minus 1. So now I have a limit statement as x approaches 1 of that. Now, what just happened? My x minus 1's canceled. My x minus 1's canceled. So now I end up having my limit as x approaches 1 of x squared plus x plus 1. This right here, this x squared plus x plus 1, is what's known as my simpler function. All right? So when I'm asking for the simpler function, this is what I want. Are you following me? Because now we can direct substitute. Okay? So when I direct substitute 1 in, guess what I get now?
3.
I get 3. All right? So now I end up getting 3. And so my answer to this limit statement at the beginning is 3. All right? So that is what we're looking for. Now, remember graphically, what just happened?
A hole.
It was a hole. At what?
1.
At 1 comma 3. Okay, there was a hole at 1, 3. That's what happened. Okay? But this simpler function is the same thing except for at that hole. That's what's really happening here. Okay? So that's what's going on when we cancel something out. Now it works. All right? Let's keep moving. Here we go. So now I have a limit as x approaches negative 3 of x squared plus x minus 6 over x plus 3. Again, what do we try to do first every time? Direct substitute. So let's do it. What do I get up top?
X plus 3x minus 2.
What do I get up top? I get what? 0. What do I get on the bottom? 0. All snap. What happened? It's going to be a hole. All right. Does that mean the limit exists or doesn't exist? No, that means I got to keep going. All right. Could it be a jump discontinuity? It could. All right. However, this one's not. All right. So, what are we going to do to the top now, TJ?
Are you sure about that? I don't think it's... F it up to x plus
We're going to F it up.
minus 2.
So now we say it's x plus 3, x minus 2. Over x plus 3. So what cancels? X plus 3 is canceled. So now I end up having this limit as x approaches negative 3 of x minus 2. And what do we call this x minus 2 thing? The simpler function. Now I can use it. Okay? These are the same things. This x squared, this original one, is the same thing as this, except for at one spot. One spot. And so now I substitute in negative 3. And what do I get? I get negative 5. All right. So my limit is negative 5. All right. Which really means there was a what going on? A hole where? Negative 3, negative 5. That's really what's going on behind the scenes. All right. All right. Let's do it. So our strategy for finding limits. Let's go ahead and read this one. All right. Ansley's going to read for us.
Learn to recognize which limits can be evaluated by direct substitution.
All right. We always try to do what first?
Direct
Substitute. All right. Keep going.
If the limit of f of x as x approaches c cannot be evaluated by direct substitution, try to find a function g that agrees with f for all x other than x equals c.
All right. Try to do something to get a simpler function. All right. Number 3.
Apply theorem 1.7 to conclude analytically that...
All right. Right now, our only other method is factoring. Right now, that's our only method. All right. And then?
Use a graph or table to reinforce your conclusion.
All right. If the factoring thing we can't do right now, we did numerically and graphically yesterday. All right. So look a little bit to the left, a little bit to the right, and see there. All right. So those are our techniques so far. All right. Start your homework. Enjoy. Who is that? Good job. Again, what do we try to do first every single time? Direct substitute. All right. So on this one, we have the limit as x approaches 0. Square root x plus 1 minus 1 over x. So if I substitute in 0, what happens?
Hole.
I get a 0 over 0. I get a hole. So I need to do something else. Can I factor this one?
Conjugate.
No, I can't factor this one, but what do I want to do?
Conjugate.
I multiply by the conjugate. Wow, that was also on the summer coursework. How about that? So I need to multiply by square root of x plus 1 plus 1 over square root x plus 1 plus 1. So my numerator now, when I do the Florida part of the FOIL, I end up with x plus 1 minus 1 over, don't distribute this, remember? So then I now have that. Well, what happens up top?
It doesn't do x.
My 1's cancel, and then now I have x over x, so now what can cancel?
The x's.
My x's can cancel. I love it when that happens. So now I end up having the limit as x approaches 0. What is my placeholder up top now? 1 over the square root of x plus 1 plus 1. All right. Now, I know some people are like, we didn't rationalize, we unrationalized. Kind of. All right. But in calculus, that's good. That's okay. All right. So now we use it. So now when we substitute in 0, what do we get? We get 1/2. All right. So again, I used my simpler function. So now I have 1/2. All right. So what really just happened? We have a hole going on where? 0, 1/2. All right. That's happening. All right, so if we looked at it numerically or graphically, that again proves our point because a limit is approaching from both sides. So if I had to make a table, that's how we could do it as well. Pretty good in the hood? All right, so those are all three techniques of how to find a limit. Now I'm going to talk about what's called the squeeze theorem. And the squeeze theorem has actually come up on the AP exam more often than I would have thought. I'm going to kind of break it down a little bit. So a squeeze theorem is basically saying a function that's always going to be up top, above it. A function is always going to be below it. And so the function in the middle, we can figure out what it is, all right, by squeezing it. Now, this is also called the sandwich theorem. Sometimes it's referred to as the pinch theorem. Because I don't know, sandwich, buns, squeeze, pinch, kind of the same. I will probably refer to it as the squeeze theorem. All right, but we have this inequality going on. All right, we did this a little bit last year, just for like a couple examples. So we'll go over it a little bit more, and then at the end we'll hit it again. All right, so on this one, I want you guys to write these two special limits down. I need you to memorize them. This first one we've kind of already proved once. So limit as x approaches 0 of sine x over x is equal to 1. Yesterday, or the first day, I guess, so I guess it was Monday. So Monday, we kind of proved it, no, it was yesterday. Yesterday, we proved it graphically, didn't we?
Yes.
And then we proved it numerically with a table. Analytically, I can't prove yet. I'm going to try to prove it with the squeeze theorem for a second. All right. There is another method that we'll learn at the end of the year that I can prove it on. All right. Right now, I have the limit as x approaches 0 of 1 minus cosine x over x, and that is equal to 0. I need you to just memorize that one and kind of trust me. Now, that was number 8 on your homework yesterday. Do you remember it being your homework on number 8? It was a table. So yesterday, we kind of proved it numerically with a table. All right? I am not proving it analytically yet. Okay? All right, so right now I just kind of need you to memorize those two. You following me? All right. When we start learning more calculus, I can prove them in other ways as well, but not yet. All right? All right, so here we go. Let's kind of bear with me a little bit. So on this one, I'm going to use the squeeze theorem to kind of prove sine x over x. And you don't have to write this down, just follow along. So if I have the area of a triangle, wouldn't you say that is more than the area of the sector, which is more than the area of the inner triangle? Everybody agree with those statements? Yes. Agreed? All right. So if I take each one of those, and I obviously would multiply it by 2 over sine. Obviously. If I do that, now I have these going on. And then, obviously, if I take reciprocals of them, I now have sine of theta over theta. Okay? Obviously, I could take reciprocals of them. Okay? And guess what? Now, if I do cosine of 0, what is cosine of 0? 1. So now I have 1 is less than or equal to sine of theta over theta, which is less than or equal to 1 when theta is going to 0. So I have 1, which is less than or equal to this, which is less than or equal to 1. So I squeezed it right there. So guess what I know of sine of theta over theta as theta goes to 0? It has to be what? 1. And that was proven to you by the squeeze theorem. Now, would anybody think to do this on their own? Probably not, and that's okay. All right, but so right now I want you to think of sine x over x as x approaches 0 is what? 1. All right, let's just go with it for now. So here we go. We're going to use it. So now I have the limit as x approaches 0 of tangent x over x. So again, what do I try to do first every single time? Substitute in. So I substitute in 0. What do I get in my numerator? 0. What do I get in my denominator? 0. All snap. What do we get? we got a hole. That means my limit doesn't, just kidding. All right, we got to keep going on it.
I don't like holes.
Well, that's not nice. You got at least like, I don't know, 5 of them at least. All right, so what do we do here?
What?
All right, I got to do something here. I got to use something that I know and kind of manipulate it a little bit. What? Turn them into sines and cosines. What is tangent? Sine x over cosine x. And then this over x thing, I got 1 over x going on. So now I have that. Well, I'm getting closer. I want to manipulate it a little bit more. How could I manipulate that a little bit more? To look like something that I know. What about this sine x thing? What do I want that thing to be over? I want that thing to be over x. So I'm going to say it's sine x over x, and then I'm going to say it's 1 over cosine x. I'm just going to move them around. All right? This is just manipulation. Girls are great at it. All right? So now, what is sine x over x as x approaches 0? What does that part go to?
1.
That part goes to 1. All right? So that part goes to 1 times, now if I substitute in 0 of 1 over cosine x, well, what's cosine of 0? 1. So now I have 1 over 1 over 1. So I have 1 times 1, which is 1. So my limit as tangent x over x as x approaches 0 is 1. You see how we use the sine x over x thing. All right, let's do it again. So now if I have a limit as x approaches 0 of sine of 4x over x. All right. Now, I need you to do this one correctly. All right. I will take off points if you get the right answer, but you get there wrong. Okay, I will take off points. So we have to be mathematically accurate here. All right. So what I want, I have a sine of 4x right now. I can't take this 4 out. Are you following me? That is illegal. All right. Even though people try to do it, and they might get the right answer doing it that way, that's wrong. You following me? So if I have 4x right here, what do I want the bottom to be? 4x. All right. But if I put a 4 on the bottom, what do I need to do? I need to put a 4 up top. Are you allowed to take out that 4 from the original? No. Don't do that. Okay. So now, this portion right here, when I take a limit as x approaches 0 of sine of 4x over 4x, that is the same thing as x over x going on. So that part goes to 1. So then I end up having 4 times 1, which is 4. All right. See how we mathematically did it correctly this time. All right. Now, if you just take out a 4, will you get 4? Yes. However, I will take points off if you do it that way. Everybody hear that?
Every time you do that, a kitten dies.
A kitten dies, you're right. All right. So true. All right, that's on the recording. That's good. All right. So this next one, I have a limit as x approaches 0 of 1 over 3 plus x minus 1/3 over x. All right. So we got what's called a complex fraction, or what I like to refer to as a fraction. All right. So again, I try to substitute in 0. What happens? We get 0 over 0. We get whole. We got to do something with it. All right?
I don't like doing the holes in math.
No. Get over it. All right. So first thing we're going to do is distribute dividing by x. All right. We're going to distribute dividing by x. So now I end up having 1 over x times x plus 3. And then minus 3. Oh, just kidding. 1 over 3x. Now, how do we add or subtract fractions? We need what? Common denominators. All right. So what does my left fraction need? Come on.
3.
My left fraction needs a 3. So I need to multiply my left one by 3 over 3. And what does my right one need? An x plus 3. Here we go.
Have Nolan go write it on the
So we multiply by 3 over 3 on the left side. We multiply by x plus 3 on the right side. So now we end up having 3 over 3x times x plus 3. And then I end up distributing the negative 1.
I can't
So now I have minus x minus 3.
Yeah.
What?
We're gonna have your
So what cancels in the numerator? The 3's cancel. So the 3's cancel. Now what can cancel? The x can cancel.
No, yeah.
So what's left up top? Negative 1 over 3 times x plus 3. Now that is my simpler function. All right. So now we substitute in 0. So when we substitute in 0, I end up getting negative 1 over 9 because it's 3 times 3. All right. Your homework. Page 68. Numbers 55 through 62, 65 through 73, 85, and 86. And you have a quiz on Friday.